All right, today we got binomial probability distributions. You know, we did probability distributions yesterday, and this is a special type called binomial, which means, two things probably. Among the different types of discrete probability distributions, there are a few that are particularly important. One of the most important ones is the one we're doing today, better known as the binomial probability distribution. Binomial distributions allow us to deal with circumstances in which the outcomes belong to two categories, two outcomes, such as acceptable, defective, survived, died, I knew this, I didn't know that, two outcomes only, and that's why it's binomial. Okay, four things must be true. You have to have four requirements for it to be binomial. Make sure you get these down. Number one, there's a fixed number of trials, meaning we're going to toss a coin 5 times. That, matter of fact, tossing a coin is binomial because there's two outcomes, heads, tails. Fixed number of trials, though. You're not going to flip forever. You're going to flip a certain number. Number two, every event, every trial is independent. One time you flip a coin has no impact on what you get the next time. They are independent. One trial does not affect the probabilities in the other trials. Number three, each trial must have all outcomes classified into two categories. We're going to say success and failure, but live, died, heads, tails. One of those is going to be considered success, one's going to be considered failure. And the last one, number four, the probability of success is the same in all trials. And that kind of goes back to number two. Everything's independent, so the probability should not change per trial. Notation. There's a lot of notation here. S and F we're going to use a lot for success and failure, but instead of using S and F, like there's S, there's F, probability of success, probability of failure. P and Q we're going to use for the probabilities. P is going to be probability of success, and Q is going to be probability of failure. So make sure you get that. P is always going to symbolize success. Q will be failure every time. There's more letters coming up. Here they are. N, little n is going to be how many trials there were. If we toss a coin, flip a coin 5 times, n is 5. X is the number of successes in trials. So like, let's say we want to know what are the chances of getting 3 heads in 5 flips. Well, 3 would be your X, 5 would be your N. P, probability of success, would be 1/2 because you have a 1 out of 2 chance of getting heads. Q would also be 1/2 because in that case, failure is the same probability of success. It's not always going to be that way, obviously, but when you flip a coin, you have a 50-50 chance. And this symbol right here, P of X, is it probably getting exactly. So in our case, if I were looking to get the chances or probability of getting 3 heads and 5 tosses or 5 flips, I'd put P of 3. Okay, so make sure you got the notation. You can see those letters over and over again. Couple words of caution here. Be sure that X and P both refer to the same category, being success. All right, so make sure they're the same. And also, like we've always said, when you're sampling without replacement, even though you're not replacing them, we're going to consider the events to be independent if this sample size is less than 5% of the population. Just like we did the other day. When our sample size was very small compared to the population, we're going to act like it's independent even though it's dependent. Okay, let's look at an example. It says when an adult is randomly selected, there's a 0.85 probability that this person knows what Twitter is, which means, there's 0.15. Now, suppose we want to find the probability that exactly 3 of 5 randomly selected adults know of Twitter. Does this procedure result in binomial distribution? The answer is yes. Here's why. There are 5 trials, so there's a limited number of trials. They're independent. One, if you ask one adult, has no impact on what the next adult says. Each trial has 2 outcomes, meaning yes, I do, or no, I don't know what Twitter is. And there's a constant probability. The probability every time you ask an adult is going to be 0.85. Those are the 4 things. Fixed number of trials, have to be independent. Each one is independent, has to have 2 outcomes, and the probability must be the same every time you ask someone or every time you do an event. Now, to solve this, you have 3 methods to solve them. The first one is using the formula, and we're going to do that a lot, but there's the formula right here. Looks complicated, it's really not. This right here, this first part, which has all the factorials, I know you probably don't remember this, but that is the exact same formula we did for NCR, except today we would use NCX. And you can use that same button on your calculator. We know what P is already. We know what X is. X is number of successes. Q is failures, and you do N minus X. So what happens is our two exponents always add up to be the number of trials. And it tells you down here what all the letters stand for again. But those are the same things we had on the other slide. Okay, method 2 is you can use the TI-83 Plus or 84 Plus calculator. They both do the same thing. I need to decide whether I want to teach you that or not on the calculator or make you use the formula. I have to think about that one. Method 3 is using a table, and I'm going to be honest with you, we're going to start using quite a few tables beginning in the next couple of weeks, so that may not be a bad idea either to kind of get you used to using some tables, but tomorrow, probably not. I'll probably decide between just the formula and also the calculator. Okay, back to our example. Given there is a 0.85 probability that any given adult knows of Twitter, use the binomial probability formula to find the probability of getting exactly three adults who know of Twitter when 5 adults are randomly selected. Here's our variables. N is 5. That's how many people we ask. 3 said yes. There's a probability of yes, which means that's the probability of no. The probability of failure is always 1 minus P. So I did 1 minus 0.85 to get Q 0.15. So we want to do this. Probability of exactly 3. So on my calculator, and I'm going to use the formula, but use the calculator at the same time, kind of. So I'm going to do this. I'm going to do 5C3. That takes care of the factorial part. Times 0.85 cubed. And the reason that's cubed was because that's the successes. There were successes go with the X, remember. The probability of success is 0.85. We're looking for 3 successes, so to get 3 there. Then you put 0.15, and this exponent on the 0.15 is basically n minus x, so 5 minus 3 is 2. These two exponents, the two exponents that I have here, this one and this one, always add up to be your n. They always add up to be that way. So if I put 3 here, I'm going to put 2 there. If I had to put 2 here, I'd have put 3 there. 4, 1. They have to add up to be the 5. Now you just punch all that in your calculator, and it's quite a bit to punch in actually. So I'm going to punch in 5C3 times 0.85 cubed times 0.15 squared, and it equals 0.138. Remember, probability, we go 3 decimal places, 3 sig figs or sig figs, and you got it. So that's pretty much all there is using the formula. And I may show you the calculator way. I have to think about that still. We'll figure it out tomorrow. Hopefully it wasn't too bad. Just one type of probability distribution, binomial. Make sure you know those requirements because it's going to come back later in the year too. So need to know it. Hope it wasn't too bad. We'll work on it tomorrow. See you then.